So our next speaker is remote, Dr. Mahdi Tavakoli from University of Alberta.
Thank you very much. Good morning to you. And do you hear me okay?
Yes, we do. If you don't mind sharing your screen, that would be great.
The previous person is still on.
You're working on it.
2 talks ago, yeah.
Wait. Meanwhile, I can say the title of the talk. So the title of the talk would be Uncertainty Aware Safe Adaptive Motion Planning for Exoskeleton Using Machine Learning.
Thank you very much. Hello, everyone. Thank you very much for being here.
Sorry, Dr. Tavakoli, can you go basically to the full screen mode, please?
Yes.
It's awesome. Go ahead, please.
Thank you for being here, and thanks to all the organizers for organizing this interesting workshop. So I'm going to talk about applications and pitfalls of AI in the area of rehab. I'm going to talk about exoskeletons, both lower limb and upper limb, and I'll talk about some other applications of robots in rehab. Some of this can be applied to the area of surgery as well, for instance, learning from demonstration. So the main motivator for much of the rehab work is the aging of population. So if you look at the graph at the bottom, right now the number of people under 5 is fewer than the number of people over 65. So this has led to an increase in the prevalence of physical injuries from falls and things like that, mobility impairments, and disabilities. And so that's why the demand for rehabilitation services is at a high, and rehabilitation from these disabilities requires neuroplasticity and lots of strength training sessions, which are very burdensome and exhausting for physiotherapists. And therefore, we have long wait times. But intelligent robots can help because they can reduce the workload of therapists through learning from demonstration. That's one thing that I'll be talking about. And also, if you have intelligent robots that adapt to the user's needs, then there is the opportunity to personalize healthcare so that on an individual and patient-specific basis, we deliver healthcare to patients. So that's what I'm going to talk about in this presentation. So let me start with the first bit, which is learning from therapist demonstration. So we want to have a physiotherapist teach a robot what it needs to do for a patient. And then if the physiotherapist leaves, and in future iterations of the task, it is possible for the robot to generalize and reproduce that motion for the patient so that the patient gets a higher dose of therapy. So rehabilitation is facilitated by the patient practicing repetitive exercises, as you see on the top right. And then the therapist is there to provide hands-on guidance, sometimes assistance and sometimes resistance for the patient to build muscle strength. As I said, this is very burdensome for therapists, and therefore robots have been developed. The robots are basically like a haptic game engine that never get tired, and the patient can get as much exercise as they want. The problem is that these robots bypass therapists and are only built for very simple and specific interactions, like reaching actions. So they cannot facilitate the performance of activities of daily living for patients. So it's believed that if activities of daily living are integrated directly into the rehab program, then the results of the rehabilitation translate better when the patient leaves the clinic. So if the patient just learns to go from point A to point B, make reaching motions, how does it really translate into being able to lift a cup and drink from it? It's best if those activities of daily living are directly incorporated into the rehab program. So that will result in better patient independence and quality of life down the road. The problem is activities of daily living are done in unstructured environments, and it's not easy to program robots to help patients with performing those activities of daily living because there is a large variation. If we are talking about drinking from a cup, well, what is the size of the cup? What is the height? From where am I picking it and where am I taking it? So the solution that we came up with was to use learning from demonstration, where we learn from a therapist's hands-on demonstration of the task and teach a robot through kinesthetic teaching what it needs to do for the patient for that specific exercise and given the specific abilities of that particular patient. So this is the area of kinesthetic teaching or learning from demonstration. We want to encapsulate the intervention and knowledge of the therapist by machine learning so that we can enable semi-autonomous patient-specific robotic intervention down the road. And this has two phases. The first one is learning, is demonstration, where a robot observes and learns from a human's actions. And then reproduction, where the robot imitates those actions in the absence of the person who showed those actions. So basically the idea is that the therapist comes in for part of the operation and helps the patient, and the robot is observing what the therapist is doing for the patient and generalizes that through some machine learning. So we use GMM and GMR methods as one way to do it. And then down the road, more doses can be provided just by the robot in the absence of the therapist, because the robot knows what the patient requires. So these are some examples. The first one at the top is a patient is engaging in the activity of the living of opening a drawer. The robot is just in impedance control mode and kind of listening and observing what the patient requires. In this exercise, now the therapist comes in and shows what the full performance of the task is. So the robot has seen what the patient alone can do, which is incomplete, and what the patient plus therapist did, which is complete, and subtracts them statistically to know what the therapist provided and reproduces that behavior in future iterations of the task. Similar one is shown at the bottom, where this patient, all of these are simulated patients, has a problem clearing his left toe. Now, using this rope and pulley mechanism, a therapist, simulated therapist, is showing a robot at what parts of the gait cycle the left part of the body, left side of the body has to be lifted. And just based on data, and without having any model for what's going on, the machine learning algorithm is able to generalize that behavior and deliver it so that the patient can keep walking for a long time. Obviously, if the patient changes, or if the conditions of the patient changes, the patient gets tired or gets better in performing the task, then you need to retrain the robot. But the idea is that with a few iterations of demonstration, you're able to get a lot of reproductions. We have used the same idea of learning from demonstration in other scenarios, for instance, for rehabilitation or assistance of children with disability who want to play this hot wire game. So a 2D version of that is here, where you want to go through these narrow openings. A person that has jerky motions is not able to play that game and therefore fails, and therefore is discouraged from trying it again. So we've used this idea of learning from demonstration, where a helper comes in, maybe a sibling, and shows the robot what sort of assistance this person requires. And as I said again, the statistical difference between the helper and the user alone is calculated and reproduced by the robot in future iterations of the task. So this is the helper. On the right-hand side, we have an actual patient. Left-hand side is a simulated patient helping them. And then later on, the person will have a much easier time performing the task successfully. You can use the same idea for telerehabilitation. So the patient and the therapist are not in the same location. Maybe one is in a hospital and one is at home or in a rural community, and they are engaging in an activity of daily living. The therapist can come in for some time, and the machine learning can learn that behavior and reproduce it. So these are the cases of using a teleoperation system for telerehabilitation. And as you see, whatever the patient is doing, the therapist is helping them. For instance, lifting the other side of this bar, or keeping this piece of wood here so that the patient could drive a screw into it. And again, the therapist is not needed once the demonstration is done and the action is learned. So that's the first part. Another application of AI in rehabilitation that I'd like to talk to you about is adaptive gait planning for locomotion of the lower limb. So here the goal is for a person with disability who is not able to walk on his or her own and is using an exoskeleton for walking, we use AI to adapt the exoskeleton to the needs of the patient. So if the patient wants to go faster or slower, whatever is comfortable for the patient, the robot understands that and generates that motion. So for generation of the motion of joints of the lower limb, CPGs or central pattern generators are used. So CPGs are a group of neurons in the body, but artificial CPGs are basically a set of equations, like a set of sinusoids that generate the motion for the hip and ankle and knee joints. So the coefficients here, this coefficient rho is basically the amplitude or the step length. And then the frequency is how fast, corresponds to how fast you want to walk. And then this offset or equilibrium is basically something that determines where the start and end angle for each joint is. So we want to be able to adapt these parameters, this offset, this amplitude, and the frequency of the CPG to the needs of a given user. How can we do? So we decided to use the physical human-robot interaction, which is basically the amount of torque the user puts forward to push the exoskeleton to accelerate, or applies in the negative direction to make the exoskeleton decelerate. We decided to use that to adjust the amplitude, frequency, and equilibrium. So that's how we're going to do it. To measure PHRI in a sensorless way, because we don't have such a sensor in the exoskeleton to measure the interaction forces, we use the neural network that we trained. So that neural network is trained, it measures or estimates the interaction torque between the human and the exoskeleton. And then we put them into these equations to calculate some energy term and some total torque term. Then this energy and total torque terms enter these equations of CPG. So basically CPG is a set of differential equations that give you the frequency, amplitude, and that offset value for the sum of sinusoids, which gives you the motion for each joint. Our contribution was adding these three terms there. So some energy terms and some torque terms are there. If the user is applying interaction or is applying energy to make the exoskeleton move faster, then the exoskeleton will understand it and move faster, or have a longer step length, or change the offset. So that's really all. And for this, we had to rely on a neural network to do sensorless estimation of the physical human-robot interaction torque. So as you see here in these videos, it's not that easy to see, but if you pay close attention, at the beginning, it's very difficult for the human to push the exoskeleton to move faster. But as time passes on, then the CPG, this adaptive CPG, is doing its work. It's estimating those interactions and then speeding up the frequency and elongating the step length, because the patient in this case was putting forward interaction. So it becomes easier, and the exoskeleton is sort of adapting to the needs of the patient. If you look at the diagrams here, the blue hip joint, the blue shows the right hip joint and the green shows the left hip joint. So with the right hip joint, the person was putting in more energy. That caused the amplitude or the step length to increase faster compared to the left hip, where they were putting less energy. Okay, so the more energy you put in, the faster the amplitude goes up. But there is a bit of defined thresholds so that the step length does not become something that's not feasible or desirable. And if you look at the frequency also, as the user puts in energy, then the frequency or speed of walking also increases, and there is good tracking of the desired motions. Now, one pitfall of the use of neural network is that neural networks are always going to predict something. So that neural network is going to always estimate or generate an estimation for the human-robot interaction torque. How do we know that it's true? The neural network may generate a prediction with low certainty. It may generate a prediction for which it's unqualified because it's not seen a comparable data in the training data set. So what we try to do in this part is do some sort of uncertainty analysis on the prediction of the neural networks or whatever deep learning model, and then use that confidence factor as a weight we attach to those energy and torque terms in the adaptive CPGs. So if we are highly certain about the estimation of the neural network, then yes, go ahead and change the CPG accordingly. If not, reduce the weight that that term has in the CPG changes. So this is done through out of distribution analysis of machine learning algorithms for calculating this model prediction certainty or uncertainty. So that's where the motivation goes. These systems are safety critical. We don't want to generate unsafe motions. And therefore, when AI is part of the brain of the robot and is involved in decision-making, it's important that we do a safety analysis. Deep learning does not provide a statistical guarantee of the predictions that it's going to make and can't handle data that's outside the learning distribution. So what we tried to do here is we replace this neural network with some random forest regression method for which we could do this out of distribution analysis. And then we generated a confidence number. And this confidence number together with the predicted or estimated torque of interaction between the human and the exoskeleton was used in shaping the adaptive CPG signals. So it's all the same as before. We have the energy terms. It's just that we incorporate this factor of certainty and confidence. So that certainty or confidence is found from this KL divergence and a distance. KL divergence looks at the distance between the distribution of the training data and the trained model's predictions. And the other distance looks at the test training set distance. So if the input is significantly different from what the network is trained for, then it generates a low score in the input space without even looking at what the model output is. So here, very quickly, these are instances where the network said, I'm not quite sure about the prediction that I'm making. Therefore, the CPG did not change significantly in response to the predicted values for the torque. Now, I'd like to move to the second part of my talk, and that is, or the last part of my talk, and that's using reinforcement learning for gait planning for lower limb and also for upper limb. So in this adaptive CPG, we had that torque and that energy term. They had some coefficients that were fixed. So those were fixed and there was no opportunity to change them. We know that there is a lot of variation between the muscle strengths of different people. And even for the same person, the muscle output changes with fatigue. So how can we allow this adaptive CPG that is initialized for one person to be usable for another person, or even the same person when the person gets fatigued? That's why we are using reinforcement learning. And reinforcement learning is basically looking at minimizing the number of times a user has to apply interaction to tell the robot, I want to go faster. Okay, so it penalizes the number of times the user attempts to say the same thing. And if the user is saying the same thing multiple times, then it amps up the gain that energy terms has in the CPG. That's basically the essence of it. And if you look at the results here, without CPG at the top, it takes about 2 minutes to converge to the desired values. but without RL. But with RL, it's much easier, much faster, about 10 to 20 seconds time to get to the desired value. So here is on the left-hand side, the results with RL, and the right-hand side without RL. The adaptation happens much more slowly when you just have this adaptive CPG with fixed gains, about 2 minutes. But when you have RL, then that gain is itself adaptive and changes depending on how many times the user is trying to convey the same message to the exoskeleton. So I know I'm running out of time. I'll be very quick. We have also done personalized assistance for an upper limb exoskeleton. So here, the goal is to use reinforcement learning to find the EMG level thresholds, because that's also something that's user specific. Each person generates different levels of EMG for the same task, so that the exoskeleton can assist the person in doing the task. And this has applications in injury prevention, for instance, among workers who have to do material handling and lifting heavy loads. So this is the exoskeleton, soft exoskeleton that we have developed. We use the reinforcement learning, and just want to show this, and then that's my last slide before conclusions. So here, if you look at her, she is trying to move these items that are heavy, like this is a bucket full of sand, and she does it with relative ease. But if you look at her other hand, it's actually much harder. It was because the exoskeleton was helping her, kind of identifying and detecting what the intention of the user was, and helping her perform that task by generating assistance that is in the same direction of motion. So reinforcement learning was trying to minimize the amount of EMG output or muscle activation the user had to put out, while avoiding jerky and unsmooth motions. So if I want to make a summary, I talked about learning from demonstration so that an expert can teach a robot what it needs to do, and the robot continues doing that. I talked about adaptation to the needs of a patient based on some physical human-robot interaction terms. And for that, we had to train a neural network, because otherwise it was a difficult task. Then I talked about how do we make it safe, because the neural network is going to always predict something, but how do we incorporate this measure of certainty and confidence in the predictions in the control loop? I talked about how we can personalize the assistance that the exoskeleton provides, depending on the muscle strength and also variations among different users. And also, finally, I talked about the upper limb exoskeleton and how it can provide personalized assistance using reinforcement learning by changing the gain by which we multiply the EMG signal to predict the assistance that a user requires in performing some material handling task. That's it. I'd like just to thank the collaborators and funders and students, and thank you so much. If you have any questions, I'm very happy to answer.
Yes, thanks our speaker, Dr. Tavakoli, for his interesting talk.
Thank you.
Any questions for Dr. Tavakoli? Meanwhile, we get prepared for the panel discussion. Go ahead, please. Yeah.
So thank you for your wonderful talk. I have a question that you mentioned that the central nervous system control the movement simultaneously. And I know that each single movement comes from the collaboration result of the multiple muscle fibers. So I wonder if we can use the machine learning to adapt this multiple muscle movement and determine the activation levels of each muscle during single motion.
Yes. So what we did was we looked at the total physical human-robot interaction, right? So when the person, and it's a combination of the output of several muscle groups that generates that interaction torque.
Yes.
As you said, we could be looking at what each muscle group is doing, and then changing that specific joint trajectory accordingly. Yes, that's possible.
Okay, so you prefer the reinforcement learning for this?
Yeah, just reinforcement learning really is one method to change that gain. So for us, the gain was fixed, and you could initialize the based on some data for one person, and it wouldn't work for another person. So people have really different muscle strengths, and in terms of how they can push the exoskeleton, and that's why we thought that reinforcement learning would be useful, because it has a reward function that can look at what is the effort that each user is putting in. And if one person is putting in too much effort and not getting enough output, well, their gain is low. The gain is low for them, right? So that is what the reinforcement learning does. It adjusts the gain for them.
Okay, thank you. Thank you very much.
Any other quick questions? All right, with that, let's thanks again, Dr. Tavakoli, and then I invite our panelists for the panel discussion.